Hello folks, this is Doug, and in this video I'm going to introduce the chemical technique called titration to you. We're just going to talk about what it is in general and talk about how to do some problems, but we're not going to get into this hardcore things about like making pH curves and calculating pKa's or anything like that. This is just to do some basic stoichiometry type problems and to get introduced to the actual technique. So titrations, basically it's a lab technique in which you use a solution that you know a lot about, you know the concentration, you know the volume, and you use it to determine the concentration of something unknown. That's how a lot of titrations are. Now, you can use it to determine the pKa or pKb of a base or an acid. We'll talk more about that later when we get more into acids and bases, but right now it's just used to determine the concentration of something unknown. And this is used in all kinds of contexts in pharmaceuticals. If you want to know how much is in a certain formulation, anesthesia, it's super important that you know how much of what compound, what anesthesia gets into a person when you're working with them. It's partially how food nutritional breakdowns are calculated, how much protein, how much carbs are in a certain protein. Food quality, like the aging of cheeses and wines, you might be looking at things like pH, how much has this cheese aged, how much has the pH dropped or increased, or various components of wines like phenols and pH also. Water quality is a big one. What does your wastewater look like when it leaves the water treatment place, or what is the water quality when it comes into water treatment, right? So you know how to treat it for when people need to drink that water. Things like acid rain, like what's going on with the pH of that. I mean, there's all kinds of like these unknown things where we want to know the concentration of a certain substance in a solution, right? That's dissolved in a solution. And then there's also other techniques that don't necessarily involve solutions, but things like, blood glucose strips or pregnancy tests. They rely on you take blood or urine, right, and you react them with a specific amount of a different reagent, and that will tell you, what the relative glucose levels are in urine or blood. Same thing with pregnancy tests, right? They're reacting with a known quantity of something, and then you're doing a test to see, well, is it above that threshold or below that threshold? So these are all examples of why titrations are important. And that's why in chemistry classes, students tend to do a lot of labs that involve titrations. So I have over here on the right-hand side, right here's a picture of a titration that you might see in a lab. Here's like probably a 125 milliliter Erlenmeyer flask, and here we have a burette. The burette is this long, tall, skinny piece of glassware. It's got gradations on it, so you can measure out to the 0.00 place, the 1/100th place. And it has a little stopcock on it so that you can add this liquid to your beaker, to your flask, and then turn it off. You can add it even drop-wise or even partial drops. I'll talk about more what that setup looks like here in just one moment. So in the lab, right, we tend to do a lot of acid-base reactions because they're pretty straightforward to do and they give you a good idea of how the technique is used. In our labs, we'll also have you figure out how much zinc is in like a cold lozenge later when we get into winter term. But you're going to see questions like, a solution of HCl is used to determine the molarity of a sodium hydroxide solution. If it takes 8.02 milliliters of a 0.18 molar HCl solution to reach the equivalence point, what is the molarity of 26.0 milliliter solution of sodium hydroxide? And that sounds really complicated and there's a lot of things in it, but the type of math that's involved is really pretty straightforward and you already know most all the concepts. The only new concept really here is how the titration thing is set up. So the idea, what we want to focus on here is you have two parts. You have the titrant, which is the thing that you know the concentration of. So I know the concentration of the HCl solution, right? And I know that it takes 8.02 milliliters of it. That's what goes in the burette, typically. So the titrant goes in here. This piece of glassware right here is called the burette. The burette's the glassware, the titrant is that solution. So that means for us, what we have up there is we have a solution of hydrochloric acid, right? In our case, it's a hydrochloric acid solution in that burette. Now what we're trying to figure out is the concentration of this sodium hydroxide thing. Apparently in here, there's 26.0 milliliters of some sodium hydroxide solution, but we don't know the molarity of it. We don't know the concentration. And so we're doing this titration because depending on how much acid I need to add in order to get it to neutralize, that will tell me how many moles of hydroxide are in that solution. Now, another piece of vocabulary here is the equivalence point, right? It says to get to the equivalence point, and down here I put determining the equivalence point. The equivalence point is when you have that when your moles of acid of H plus equal your moles of whatever it is that you're looking for. In our case, it's hydroxide ions. And in a lot of acid-base reactions, it's going to be hydroxide ions. So your equivalence point is usually when those two are equal. And since when those two are equal, you hit a pH of about 7, we see these a lot with these neutralization reactions. But what's really important for us is this key fact. It's when the moles of acid and when the moles of base are equal. And there's different ways you can determine this, right? You can use something like a pH meter. It's a probe that you'd stick into this flask while you're doing the reaction. And that just tells you on a computer what the pH is at any given time. So as soon as you hit a pH of 7, boom, you know you've hit the equivalence point and you've added the same numbers of moles of acid as you have base. What's more common, just because pH meters are expensive, they can break, they need to be calibrated. Another easy way to find the equivalence point is to add a chemical indicator that will change colors for you at the pH that you want. So if you're doing a neutralization, you want something that changes at after a pH of 7. You'll notice that the solution is a little pinkish, and that's is because of the indicator that they added. So let me just talk briefly about indicators. Again, we don't have to go crazy into them, but I just wanted you to see kind of what we're talking about. Here's something from Wikipedia. Here's a bunch of different indicators. There's way more than this. But the idea is that indicators are dyes that change colors at different pHs. You may have, when you're younger, done that cabbage pH indicator where you take red cabbage, boil it up, add things like baking soda or lemon juice to it, and you can change the colors of the solution. Same thing here, right? So like bromothymol, oh, that's bromo, not brome. That's a typo. Bromothymol blue is yellow when you're below a pH of about 6.5. And then it turns to green because you're moving into blue. And so above a pH of about 7, it's very blue. And so you know that when you see the color go from yellow to blue, you've gone through this pH range, even though you don't have a pH probe in there. You can tell by the change of color that you've gone past 7, for example. Something like this, though, can be kind of tricky because you're like, wait, how green is green? Is that green? Is that green blue? Is that green blue? I mean, it's kind of hard to tell with those things. What we're going to see in lab is that we like to use phenolphthalein a lot because it's pretty easy to see clear colorless and all of a sudden pink show up. So here's flasks where you have you're adding the indicator, but it's all clear, right? So that must mean we're below a pH of about 8.5 or so. We're below, it's right. Phenolphthalein has no color when you're at low pHs. And don't worry about pHs too much. I'm just trying to give you an idea of how these things work, how you're going to do it in the lab. And then once you get to the point where you're just starting to change colors, that's when you know you've reached your endpoint here. See how this is slightly pinkish, whereas that was colorless? And then if you get real pink, right, that's much darker pink, that means you've gone way over here. You're way past that equivalence point. You've added too much of your hydrochloric acid, for example. Or I guess in this case it would be base, but it doesn't matter. You've added too much of your titrant. You've gone past the equivalence point, and now you're really basic. You're past this point. So for example, when you do this in lab, you're going to be aiming for like the slightest pink color, like just barely pink. Like you're going to be asking yourself, is that pink? No, I'm pretty sure that's pink. That's perfect. That means that you've just gone past a pH of 7. You're at a pH of 8, so you've reached the equivalence point. So that's how we kind of determine this equivalence point. But the point of the equivalence point is just that you have equal moles of your acid and your base. That's the key piece that you need to solve titration problem. So let's look at that problem that we had before, right? The solution with HCl's, we're trying to figure out the molarity of a sodium hydroxide solution. Now, the question, right, is asking, what is the molarity of this sodium hydroxide solution? So like we talked about in previous videos, right, we know that whenever you need to solve for molarity, that's moles over liters. And you have two problems then, right? This is moles, I'll put NaOH. Moles of NaOH over liters of the NaOH solution. And we talked about before that when you have these problems, really you have two problems. One, you need to figure out the moles. Two, you have to figure out the liters, and then you just put one over the other. This one's kind of nice because I can already figure out the volume because I know that there's 26.0 milliliters of this solution based on this. And I know that I just need to divide that by 1,000, right, to turn that into liters. 0.0260 liters. So real easy. It's real easy for me to figure out, right? It's real easy for me to figure out how many liters there are. That's easy. What I don't know yet is how many moles of hydroxide there are. So that's really the thing that I need to figure out. I need to figure out how many moles of hydroxide there are. Now, to approach this, we need to use stoichiometry. I know that I have an equation, I have a reaction between HCl and NaOH, and so I need to do what I do for all stoichiometry problems, which is to write out a balanced equation. This says we are taking HCl and we're adding it to sodium hydroxide, NaCl, which makes water. Right? And if you don't remember how to do these, go back and look at the acid-base reaction video. All right, we're just doing a double replacement, replacing the Na with the H to get HCl and HOH, or in other words, water. Make sure it's balanced. Looks like I'm already balanced. It's just a 1 to 1 to 1 to 1. Everything's balanced here. And then I'm going to set this up like I normally would for just a stoichiometry problem. Right, so I'll go ahead and I'll write out my known. What's my known amount that I'm starting with? And this might get a little cramped, so I apologize in advance. My known amount from this equation that I haven't dealt with yet, my known amount here is, it says it takes 8.02 milliliters of this solution, of this HCl solution, this hydrochloric acid solution. So that's my starting amount, is the 8.02 milliliters. Remember that big M, and I'll just put it down here now since we're talking about it, that big M, that 0.18 big M, that's molarity, that's molar. And that always equals moles per liter. So saying that is the same thing as saying 0.18 moles of HCl per 1 liter of HCl solution. Right, that's what that's saying, right? This does equal, right, this is the molarity. That is the molarity. And I just got that from the equation. It flat out told me that. What am I looking for? Well, we already said that what we're looking for here is we're looking for moles of NaOH, because I cannot figure out my molarity of NaOH. I cannot figure out my molarity of OH until I figure out how many moles of NaOH there are. So I'm really kind of solving for this. So I'm going to do all this stoichiometry just to figure out how many moles of sodium hydroxide there are. And then I'll ask myself, well, what other conversion factors do I need? Since this is stoichiometry, I need a mole ratio between the two things that I'm concerned about. I'm concerned about I start with HCl and I'm getting to sodium hydroxide, so I know my mole ratio here is going to be 1 to 1. I know that I have 1 mole of HCl for every 1 mole of NaOH, right? And that's fair to say, especially because we're going to the equivalence point. We know we have equal amounts of them. And I don't know, do I need anything else? Well, I'm starting in milliliters, but molarity is in liters, so maybe I need a 1,000 milliliters to liters, right? So I can convert that. I don't see anything saying anything about grams, so I'm not going to put any molar masses yet, but maybe I will need a molar mass. We'll see. We'll see. Let's start putting this together. So my starting amount is 8.02 milliliters of HCl. I should have put that up there, of HCl solution. I'm going to convert those milliliters into liters so that I get liters of HCl. And I see here that for every 1 liter of HCl, there is 0.18 moles of HCl. And I know for every 1 mole of HCl, apparently there's 1 mole of NaOH. Right, so I'm just using these conversion factors, right? I use that one, then I use that one, then I use that one. I'm just following the things so that I get moles of NaOH, right? That's the number I need to figure out the molarity up there. So if I do all that math, right, I take 8.02 times 0.18 divided by 1,000, I get 0.00144. So that is the number of moles, right? This is the number of moles that I need to plug in up here. So apparently I'll erase my question mark. It's not a question mark anymore. I do know how many moles of sodium hydroxide there are 0.00144. And now I just take 0.00144, divide that by 0.0260, giving me 0.0555 molar. That would be my final answer, right? That is the molarity of this sodium hydroxide solution. I determined it because I knew I mixed it with the reagent that I knew the concentration of. And so I could just deduce, because I know the mole ratios between the two in an equation, what the molarity or how many moles were present in that final solution. So this isn't really all that different than stoichiometry problems that you've done before. The biggest difference is that you're going to start with a volume and then you're going to end wherever you end. It might be that someone asks you for moles, it might be someone asks you for molarity or for grams or whatever the context is. You just would add another conversion factor if you needed it. So let's look at this question in a slightly different way, right? Here's back to that unit conversions roadmap thing. The problem that I just did, we started off in milliliters, so maybe I should add an extra little box here. I went from milliliters to liters, right? And that's just your 1,000 to 1. But I went from milliliters to liters. Since I was in liters, I could figure out how many moles there were using the molarity, right? The molarity is kind of the new thing in this chapter. You need to know molarity in order to do these. But I didn't want to know the moles in that solution. I wanted to know the moles of a different thing, right? Moles B, which is why I used that mole ratio. And then once I had moles of the other thing, in this case it was the hydroxide solution that I didn't know, then I was able to solve for something else, namely the molarity. So I'm still using this unit conversion roadmap, right? This is how you get from one point to another point. All these things are really, really connected. And it could be, for example, there's no reason why you couldn't have started off with liters of some solution and then you did some mole conversion to get a different thing, and then maybe you found the mass of it. Maybe I wanted to say how many grams of sodium hydroxide must have been in that solution, and I could have gone that route instead. I'd just use a different conversion factor, or in this case, add a conversion factor. So with this in mind, let's do a few more examples. So here's another one. If 42.9 milliliters of a 0.66 molar solution of potassium hydroxide are required to neutralize 20 milliliters of hydrobromic acid, what's the molarity of the HBr solution? So this is very similar to that first one, right? Very, very, very similar. So you can pause at this point and take a crack at it, see if you can set it up the same way. I'm going to go through it too. So pause right now if you want, or we'll do it together. I have a couple more examples that I want to do with you. So this is not the last. So first things first, it's asking what is the molarity of HBr. And again, I know that my molarity equals moles, in this case HBr, per liters of my HBr solution. And I need to figure out those two things. Easy enough for me to figure out the liters because it flat out tells me, right? It flat out tells me that there's 20 milliliters of the HBr solution, so I can convert that into milliliters. I'm being lazy for the sake of speed here. But right, you just take 20 divided by 1,000. And the thing I don't know right now is I don't know how many moles of HBr there are. So here comes the stoichiometry. Set up your equation. I've got my equation here. I've got potassium hydroxide mixing with HBr. I can tell already that's going to be a 1-to-1 ratio. But I'm going to get KBr plus H2O. And sure enough, it's all balanced, 1-to-1 ratio. So I do the same sort of thing where I set up my initial, or my known, my unknown. Conversions. So the known amount for this one, right, this thing that we're starting out with that we know for sure is all this information about the potassium hydroxide solution. So I know that there is 42.90 milliliters of my KOH solution. Now don't get that confused again with that 0.66, right? Remember that 0.66, that big M stands for molarity. I'll go ahead and I'll put that in right now. That molarity thing, right, that 0.66, that's how many moles of KOH are in 1 liter of my KOH solution. So I'll just go ahead and get that out of the way, right? That's the molarity. All stoichiometry problems involve mole ratios. So let's just do ours right here. So 1-to-1 again. The next ones I do, by the way, are not going to be 1-to-1. I'll give you things that are slightly different. I might as well mention this now while I'm thinking about it. In this case, they're all 1-to-1 ratios because you have what are called monoprotic acids and monobasic bases, right? So this acid only has one H, hence the term monoprotic, mono meaning one. We'll see that there are acids that are diprotic acids, right? They have two hydrogens, so like sulfuric acid is a common example, H2SO4, or triprotic, like phosphoric acid, which is H3PO4. So our stoichiometry is going to change when we deal with diprotic or triprotic acids. So we'll see an example of that coming up next. Don't you worry. So I've got milliliters, and it looks like for this one also I'm going to need the milliliters. 1,000 milliliters for every liter. Sorry, because I'm starting in milliliters. And I think I have everything that I need. So I'm going to go put these together. Oh, what am I looking for? Sorry. What am I looking for? I'm looking for, right, moles of HBr. That's what I need in order to answer the question of what's the molarity. I need to figure out this numerator. I need to figure out how many moles of HBr there are in that solution. That's why I'm doing the titration. So I start off with 42.90 milliliters of HBr solution, but I can convert that into liters because I know there's 1,000 milliliters in a liter. And then once I know how many liters of solution there are, I know that for every 1 liter of KOH solution, there is 0.66 moles of KOH. I also know that for every 1 mole of KOH, there is 1 mole of HBr, because that's what my equation says. And that's as far as I need to go, because I'm looking for moles of HBr. So, sorry, not moles of HC. Z, you gotta watch yourself. What did I do here? Potassium hydroxide. Oh, that was my problem. See up here? And this is good, right? So if you look at your units, you can see when you make a mistake. Luckily, I don't think I made a math mistake here, but I accidentally wrote 42.90 milliliters of HBr when I should have written KOH. So that was that's an easy fix. I just got to erase this and put KOH. And everything else makes sense, right? I should have been crossing off my units. Milliliters, KOH, KOH, liters, moles of KOH, moles of KOH, moles of HBr. That's what I'm looking for. And if you do all of that math, let's see, what do we get here? We get 0.028 moles of HBr. So now I get to take that and plug it in up here, right? So I'm going to erase my question mark because it's no longer a question mark. I know that it's 0.028 moles of HBr. Remember that mole is little mol, molarity is just a capital M. And then I can just solve that. Divide 0.028 by 0.0200, and we get 1.4 molar. That's the molarity of my HBr solution. And that's how we'd solve that one. So let's look at a diprotic. So here's a third example, right? So now this is saying if there's 18.23 milliliters of a 0.1007 molar solution of hydrobromic acid, are required, saying if that many milliliters are required to neutralize 20.0 milliliters of magnesium hydroxide, which is and acids, how many grams of magnesium hydroxide were in solution, right? So now I'm not being asked to find molarity, I'm being asked to find how many grams, right? How many grams of magnesium hydroxide? So I can just treat this like a normal stoichiometry problem, right? So where I have, if it's stoichiometry, I gotta first do my equation. So I've got hydrobromic acid, and I've got magnesium hydroxide. Don't forget how to name these things, because as you can see, we need to be able to write out their formulas. So if I balance this sucker all out, looks like I need 2 HBRs, I make 2 waters. Yep, should be all balanced. Yeah, 2 bromines on either side, 1 magnesium on either side, 2 elements of water on either side. Perfect. So, unknown. So I've got my known, unknown, conversions. The known amount, the only amount here that we're talking about, we are starting, right, the thing that we know everything about is the hydrobromic acid. So we're going to put 18.23 milliliters of HBr. That's the thing we know about, the thing that we have the molarity of. So I'll go ahead and I'll put the molarity down here also with 0.007 moles of HBr per liter of HBr. What are we looking for? We're looking for grams of magnesium hydroxide. What am I always going to need? I'm always going to need a mole ratio because this is stoichiometry. So I know everything about HBr, and they're asking me about grams of magnesium hydroxide. So I use that mole ratio. Now notice that because there's 2 hydroxides in every 1 unit of magnesium hydroxide, that changes my mole ratio, right? Because I need 2 things of acid to react with 1 thing of magnesium hydroxide, but that's because there's 2 hydroxides for every 1 magnesium hydroxide. So my formula, right, so my mole ratio here is going to be informed by my balanced equation. So I know that there's 2 moles of HBr for every 1 mole of magnesium hydroxide. So again, we're just following what the equation says. I've got molarity right here, and I've got my mole ratio here. Much like the other ones that I've done, I got to use my 1,000 milliliters per liter conversion. And now this one is actually asking about grams. It's asking about grams of hydroxide. So I need to be able to figure out how to turn that mole of hydroxide into grams of magnesium hydroxide. So I would add up all those components of magnesium hydroxide, 1 magnesium, 2 oxygens, 2 hydrogens, and that equals 58.3197 grams of magnesium hydroxide. Right, realistically, if you're doing this at home, just Google it, but for tests and stuff, be prepared to show that you know how to do it. And I think that's all I need. So let's start. I'm starting with 18.23 milliliters of HBr. Well, let's go ahead and convert that to liters. Now that I'm in liters, I know that for every 1 liter of HBr that there is 0.1007 moles of HBr. And here's where our balanced equations really come in handy, right? If I didn't balance my equation, I'd be off by a factor of 2 here, because it takes 2 moles of HBr to neutralize 1 mole of magnesium hydroxide. And once I know how many moles of magnesium hydroxide there are, I can just figure out, right, based on the molar mass of magnesium hydroxide, how many grams I should get. So if I do that math, I end up getting 0.2223 grams of magnesium hydroxide. So that would be my answer, right? They're asking for grams. No one asked about the molarity of the solution. So in this case, this is kind of like a little red herring. This 20 milliliters, no one cared about the concentration, right? Asking about the number of grams is not asking about the concentration of magnesium hydroxide, so I didn't have to use it. I didn't use it in malaria. I didn't use it for anything. So it's just kind of floating there, which is super confusing for students, but is really irrelevant, right? Because if you ask about number of grams that are in that solution, you know, if you threw, imagine it the backwards. Imagine if you threw 0.2223 grams of magnesium hydroxide into a piece of glassware and you added 10 milliliters of water to it, or you added 100 milliliters of water to it, or 1,000 milliliters of water to it. You didn't change the number of grams in that solution, right? It's the same number of moles, the same number of grams in that solution, regardless of how much water was in there. Now, the concentration would change depending on how much water is in there, but the actual amount of stuff is still there, right? If you throw in a tablespoon of salt into a pot of water, you have a tablespoon, you still have a tablespoon of salt in there, even if you fill that pot of water halfway or all the way up, right? It's not like the volume changes the amount of salt that you poured in. So I didn't really care about the volume in this case. Just kidding. That's not how many grams. What I meant to say was 0.0535 grams of magnesium hydroxide, right? If you do all that math, you should get 0.0535 grams, 3 sig figs. That's how many milligrams of magnesium hydroxide would be in solution. Now, one last one. I know this is going kind of long, but if you want to take a crack at this one by yourself, good place to pause. Also requires a equation and everything. So pause, take a crack at this one. Good luck. So this one phrases the question slightly differently. It's asking what's the volume of a 0.47 molar solution of sulfuric acid that is required to neutralize a 1.220 milliliter, 122.0 milliliters of a 0.0500 molar solution of NaOH. Start with the same place. What's my balanced equation? So we've got H2SO4 plus NaOH. It's going to make water and sodium sulfate. And 2 waters, 2 bases. So I've got that all figured out. What's my known amount that I'm starting with? What's the unknown that I'm looking for? My known amount here, the only amount that's given is 122 milliliters of the NaOH solution. The unknown that we're looking for is what volume of the sulfuric acid. So I need to find the milliliters, or it just says volume, so I'm just going to go with liters. Saves me a step. Pay attention if someone's asking for liters or milliliters. This one didn't say, so just leaving it in liters is going to be fine. And then I want to put in my conversion factors, right? I know I have I have 2 molarities given here. Yeah, I have 2 molarities given here. So I've got, let's see, I've got a 0.47 moles of H2, oops, not 3, H2SO4 over 1 liter H2SO4. I also have the 0.0500 moles of NaOH for every 1 liter of NaOH. I have my good old mole ratio because I'm trying to do a reaction between this and this. Those are the 2 things being asked about. So I want to keep in mind that for every 1 mole of sulfuric acid, it's going to require 2 moles of sodium hydroxide to neutralize it. And I don't see anything about grams, but I do see milliliters and liters, so I might need my good old 1,000 milliliters per liter. And let's see where we can get. So, starting amount, 1220.0 milliliters of NaOH. I once again know that there's 1,000 milliliters in a liter. For every liter, 1 liter of the NaOH, apparently there is 0.0500 moles of NaOH. Now that I'm in moles of NaOH, I can use my mole ratio. So I know that there's 2 moles of NaOH required to neutralize every 1 mole of H2SO4, because that's what the equation says. And I'm looking for volume. If I know how many moles of H2SO4 there are based on the molarity of H2SO4, I can say, oh, well, for every 0.47 moles of H2SO4, that'll be 1 liter of solution. And again, since this said just what volume, I just went with liters. I don't see any real reason to change it into liters, but I can at the end. And then I would just solve for that, right? All my units should cancel out. I've got milliliters and liters, hydroxide and hydroxide, liters and liters, moles of hydroxide, moles of hydroxide, moles of sulfuric acid, moles of sulfuric acid. I'm left in liters of sulfuric acid, which is what I wanted. So if I do that math, I end up getting 0.0064 and I guess 9 to keep my 3 sig figs. I can only have 3 sig figs. Well, actually, I only can have 2 sig figs. Excuse me. So 6.5 liters of H2SO4. If they'd asked for milliliters, you could just change that to milliliters and say 6.5 milliliters of H2SO4. Well, anyways, one of these would be the answer. So for these titration problems, treat them like stoichiometry. Just know that you're going to use molarity to get into moles, and then you do your mole-to-mole ratios to answer the question. So practice this. It is math intensive, but it's super doable. Study up. Good luck.